This conference will now be recorded.
Hello, everybody. Jordan Girth here from the National Weather Service Office of Observations. Thank you for joining us for the Satellite Book Club Seminar Series. This is session number 90. Hope your spring is off to a good start. Today's presentation, monitoring the recovery of the ozone layer. We're pleased to be joined by Dr. Larry Flynn, research scientist and ozone team lead at NESDIS STAR. The facilitator for today is Linda Gilbert, lead meteorologist at the Weather Service Forecast Office in Marquette, Michigan. Just a few reminders that this session is being recorded, so you'll be able to share it with your colleagues that aren't able to join us today. There will be an opportunity for questions and answers after the presentation. We particularly encourage questions from our field offices and regional headquarters. So please place them in the chat and we will field them through there. We also encourage attendees to sign in with your full name, or if you're using an office account, please specify your full name when asking a question. That will help us get back to you if we need to. We're also looking for future presenters, so if you have an application you'd like to share with the field, we'd love to have you. And the training team can help create training materials that may be unavailable or you may be unaware of. Brian Mata at the Office of the Chief Learning Officer can help with your questions regarding that. I'd like to thank the TowerS team, particularly Kashad Bowman and Lee Byerly, the Office of the Chief Learning Officer and the GOZAR JPSS program for their support. I'd also like to thank our presenter, facilitator, and all of you for joining us. Without further ado, I'd like to introduce Dr. Larry Flynn, who for the last 26 years has been a research scientist with NOAA NESDIS. His duties include research analysis for validation, algorithm development, and calibration of existing and next generation satellite ozone sensors. Larry, welcome to the book club.
Thanks. If I'd known you were at 90, I would have postponed it for 10 more, so I could have been the 100th, but I missed my chance. Also, I apologize if I have a little bit of coughing during the talk. My allergies seem to have kicked off early this year. So today we're going to be talking about the ozone layer, and I'm going to actually do an overview of some of the things that we do in the way of remote sensing. So next. I have normal disclaimer for any talk I give where I'm saying that I'm not speaking officially for NOAA. Next. And if you want to read my abstract later, but we'll be talking about all this so I can cover it as we go along. Next. A very brief outline. I'm going to talk some about what we do for remote sensing for space-based observations of the atmosphere. And then I'll talk in particular about some records that were continued by our newest instrument for NOAA, the Ozone Mapping and Profiler Suite that's in the JPSS program. And then I'll show what I hope is good news that we are on the way to recovery. Next. So when we do remote sensing from space, we're pretty much limited. We've got to measure somewhere in the electromagnetic spectrum. We have to measure radiation coming from the Earth. We want to see how it's interactive with the atmosphere, so we have to pick what wavelengths we work with. We can vary it by, again, the wavelength, the source of the radiation, the viewing geometry, the physical path the radiation takes going in and out of the atmosphere, the orbit of the spacecraft, and some other things. And I'll just very briefly give a high-level overview of these classifications. Next. So the electromagnetic spectrum, we're used to seeing visible light, which is there in that little range in the middle. And we go from above that to infrared, to less energetic, longer wavelengths. And below that to ultraviolet, to more energetic, shorter wavelengths. And we continue on out that on both ends, going to longer wavelengths and even shorter wavelengths. I'll be talking mainly about instruments that are using ultraviolet light and backscattered ultraviolet from the atmosphere. Ozone is a very good absorber for ultraviolet light. Fortunately for us on the Earth, we don't want those high energy ultraviolet rays to reach us here on the Earth. And so that'll be where we're working down here where the little oval is in this plot. Next. So I've shown a spectrum here. The blue is the spectrum at the top of the atmosphere. So we're looking at what's coming in and going out of the atmosphere. The red is what actually comes out. after it interacts with the atmosphere. This is for one particular formulation, one particular observation case. At the very bottom here are the shorter wavelengths down in the ultraviolet. And you can see inside this oval that there's the blue line is considerably far above the red line, which, as I said, is fortunate for us because ozone absorbs most of that radiation before it gets to us. There's other places here where you can see things like carbon dioxide around the middle of this red curve in the top plot, where carbon dioxide is affecting what goes on in the atmosphere. And so there's a lot of different things going on with the transmission and absorption that takes place. So when we're out in space, we see the results of this, and that's how we see what comes out to give us the information that we can use. So next slide. So again, we need to have a source. In the case of the instruments I'll be discussing, our source will be the sun. So those are passive methods that use the existing natural sources. And there's also methods that can use man-made sources, such as radar or LIDAR. And I won't be discussing those. Again, I've listed some active sources at the bottom here, but we'll be talking mainly about things that use sunlight, ultraviolet or visible, that gets reflected or scattered by the atmosphere. As it goes in and out of the atmosphere, the different wavelengths are affected differently by ozone absorption and other interactions. And that's what gives us the information and the signal we get up at our satellite. I've got some slides on here I'm not showing today in the interest of time that go into what the ozone absorption looks like in various regions. Ozone's very active in the ultraviolet, but it's also active out in the visible. It also has some emission in the infrared and some emissions in the microwave. And sensors have been made to take advantage of all of these different regions to get out the information from what goes back to space from the Earth's atmosphere. Next slide. So again, there's different viewing geometries. Usually we think of having something that flies over the Earth and looks straight down. So satellite looks straight down with the Earth in the background. And it may be a wide swath that gets us good global coverage as it goes orbiting around the Earth. We also can look through the Earth at something. We can look through the Earth at the sun or the star. And this is called an occultation measurement, where we're looking through it at the source. A third one can look at the limb without a source behind it and just see what's scattered or what comes from the atmosphere itself. And the two geometries, the occultation and the limb viewing, gives the highest vertical resolution of the atmosphere if we make those measurements correctly. So next slide. This is a little bit busy slide. We've got a satellite at position A that's looking down directly at the Earth. It might have a wide swath field of view, so it can see a lot of the Earth. We've got a satellite green at B, where it's looking at limb emissions. It's looking at the Earth and seeing, in this case, perhaps scattered sunlight that could occur anywhere along this line of sight, the dashed line. And then at C, we have an instrument that's going to be using occultation. It's looking through the atmosphere at the sun, perhaps, and it sees sunrise and sunset as the satellite C orbits around the Earth, or it might be looking at GPS. There's other things that are doing that. I won't be discussing those here. So we've got these three geometries for how we could measure things. Ozone uses all three of them to good effect, the ozone measurements that we make. Next. And then we have the spacecraft orbital path and how often we see a place on Earth, how we're orbiting, whether we're in something called a near polar sun synchronous orbit, like most of NOAA's polar satellite, whether we're in geostationary orbit, like we know goes west and goes east. And again, if we have a near polar one, we have an orbit of about 100 minutes, and over 14 orbits, we see the entire globe passing underneath it as the Earth revolves under our orbit. Of course, as we know, the geostationary is designed to stay above one place and make very continuous measurements of that one location with a good view of the Earth. Next slide. So just a very quick schematic of the satellite ground track for a polar orbiting one with the Earth revolving around it and designed so that it passes over the equator at the same time of day each day. Next. As opposed to geosynchronous that follows around the Earth and as it rotates, so it's always looking at the same part of the Earth. And then one on our next slide, we've got a very interesting one. This is looking from a Lagrange point 1, which is about 1 million miles towards the sun, where the Earth's gravity balances the sun's gravity. So even though you should be orbiting quicker than 1 year, you slow down because the Earth is pulling you back out, and you stay there looking at the Earth. There's a little, I guess, Easter egg, I'll call it, in this figure I'm showing, a time lapse of looking at the Earth from Lagrange 1 in 3 channels made to give a visible look. And I'll let people discuss what that, maybe you can put in the chat what you think the Easter egg that's hidden in this sequence is. Next slide. So what is going on with the atmosphere for ozone? So back in the 70s, there were very good guys, good chemists who theorized that chlorofluorocarbons would get up into the stratosphere. They were stable molecules. They'd break down there, releasing chlorine, which would cause damage to the ozone layer. And they were right. And we launched satellites to see and make measurements and see how right they were and what was going on. And I listed some of them here, the TOMS and the SBV, and NOAA picked up the SBV program in 1985. And then there was an unexpected thing that occurred, the ozone hole. And this was halogen chemistry occurring in the lower stratosphere on polar stratospheric clouds. And the chemists got busy and did tests in the laboratory and did observations. We launched new types of instruments, and some of these were occultation ones, and some of them were limb ones, and some of them were the backscatter ultraviolet that are nadir viewing. So I've got them coded here with the colors. And so we launched new instruments like the microwave limb sounder, and SAGE is a solar occultation instrument. And then TOMS and SBV, as I said, are downward looking backscatter. So we started investigating this new unexpected chemistry going on with ozone in the atmosphere and ozone destruction. And then a third one was found where it turned out that there was halogen chemistry on aerosols. In particular, if there were eruptions with large amounts of stratospheric aerosols, sulfate aerosols, there'd be ozone destruction on these. So I want to point out that it wasn't that we had chemists saying something could happen and they were right and we understood everything at the beginning. The laboratory of the atmosphere conducted its own experiments and we had to catch up. So even though we thought we knew what would be going on and that there'd be some amount of destruction in the upper stratosphere, we didn't really have it all right. So next. So now where are we? Well, the ozone layer is recovering, and I'll show a little bit about why that's happening. We've got the EUMETSAT with some new instruments. We've got the NOAA JPSS program with some new instruments. We've got follow-ons to older instruments. For example, there's a SAGE 3 instrument on the International Space Station, and I haven't even listed them all. There's other ones. There's other instruments that are being launched by China and other people to still measure ozone. And they've increased the range of atmospheric chemistry products they're measuring by a considerable amount too. So it's not just ozone, there's other types of chemicals in the atmosphere that have absorption spectra or emission spectra that are being looked at and worked on. There's in particular, there's a Canadian four-way transport spectrometer that does occultation with the sun that measures hundreds of species of different chemicals and what it sees. Next. So we'll stick with our simple one that's designed primarily to measure ozone, but also can make measurements of other things. It's got a limb instrument that has 3 vertical fields of view that are shown here, called the limb profiler with the LP label. And it looks back at the limb of the Earth and gets out a high vertical resolution of the radiance coming from that to get high vertical resolution retrievals of ozone profiles. It's got 2 nadir sensors that look down, a nadir profiler and something called a total column or nadir mapper. And it looks straight down, and it's got a small field of view at the center where it gets a range of measurements that give us ozone profile information by sounding out the variation in ozone absorption. It's got a wider field of view that just gets total column ozone that just uses a limited number of channels to get that product. But it has full daily coverage. These all require sunlit Earth. They're all looking at backscattered solar ultraviolet, or visible in the case of the limb, also goes out into visible in near IR. Next slide, please. So what happened? Well, very fortunately, as I said, the chemists in the 1970s said something's going to be going on with their atmosphere with what we're putting into it. There was a Vienna Convention on the Protection of the Ozone Layer in 1985. It was followed on by the Montreal Protocol in 1987. And as things developed, and we saw in the mid-1980s, development of the ozone hole and other damage, there was additional things done to phase out ozone depleting substances, ODS. These are all links here on these different agreements that went on and expanded the countries in the world and how quickly they would phase out the chemicals that were affecting the atmosphere. And we even had the recent one in the Kigali amendments because there were various things done by industry. Very fortunately, industry responded to this challenge and found replacements for what we were using for the halogens and the CFCs that were being used for the old hairspray aerosols and for the old refrigerants. They found new chemicals that would not damage the ozone layer and put in that. But again, it's been long going and getting these in, and there were agreements made so that developing nations could continue using some of the chemicals longer. So let's go to the next slide. So this is an effective stratospheric chlorine slide. So if we take all these different chemicals listed on the legend, and we see how much of them is in the atmosphere, back before 1980, we were pretty much stable. We weren't really very much. And then various chemicals started being made and released as end product, or just as after the refrigerator they were in was put in the junkyard. Wherever it came from, these got into the atmosphere. They were very good chemicals because they were stable and wouldn't poison us. But because they were stable, they would be distributed in the atmosphere and get up in the stratosphere where the stratospheric ozone layer is. And we can see over time, going from the 80s, from the 60s to the 80s to 2000, we continually increased the amount of these that ended up in the atmosphere, with a peak somewhere around 2000. And you can see the growth rate of them in the atmosphere, this overall top of this line of all of them summed together, went up very quickly. And now since 2000, it started to come down, but you can also see it's come down very slowly. There's a level listed here at about 2.01 ppbv, which was regarded as a sort of a trigger level, below which we'll stop having ozone holes. But we aren't there yet, obviously. We have a ways to go. Fortunately, the countries of the world are following the agreements and keeping with their reduced production. Next slide. So this is a slide I call the ozone anomaly time series, that the picture is worth 1,000 words. I won't say quite 1,000 words on it, but I could. So this is what we were able to measure. So starting with the SBUV instrument, there was a Nimbus 7 instrument going to NOAA 9 instrument, going through NOAA 19, going to the SMPP, follow on with OMPS, going to JPSS. We've been measuring total column ozone. This is a time series from 1979 to 2019. Along the bottom, it's an ozone anomaly. It's an anomaly of monthly values that are made for 10-degree latitude bands. That's our y-axis, is latitude. And we take these time series of 10-degree monthly values, and we take out at each latitude the annual cycle, because ozone varies during the year. We take out that annual cycle and see what we're left with. And what we're left with are percent differences that range from 25% for this brown color to minus 25% for this light purple color. And if we look at this, we can see over time what's going on. There's a couple of other things going on. There's some black lines, vertical lines, where we don't have a record for that month. The satellite record isn't complete entirely. There's missing things at the high latitudes where the sun isn't present, where we're in polar night. And you can see around 1992, those actually go up even farther. And that's because our satellites drifted. We didn't have control on them, and the equator crossing time drifted, and we missed coverage. But now getting into the actual data, we can see that in general, the highest values, the oranges, are at the beginning. The lowest values are here in the middle, in the 90s, the blues predominantly. And then we start to come back up towards the lighter blues and the yellows as we go on. So this is the overall trend, and it's different at different latitudes, of ozone decreasing and starting to recover. And again, it hasn't come all the way back up in recovery. And we can see that there's more going on at mid-latitudes than at the equator. And it's hard to see, but down at the very bottom, there's some purples down in the southernmost areas, and that's actually the ozone hole. I'll show from a little bit better point of view in just a minute. We also see that there are variations. That's because there's a seasonal dependence to the ozone destruction. There's also things like in 92, there's some blue in the northern hemisphere, which is after Mount Pinatubo put a lot of sulfate aerosols, another method of destruction. And we can see that at the equator, there's not really all that much going on, but an up and down that if you look carefully seems to be at about 2 years, 2.5 years, which is a quasi-biennial oscillation in the atmospheric elevation and descent that affects the ozone amounts. So this little circle at the very end is because we had an unusually cold winter where we saw some ozone destruction in the northern hemisphere that you may remember seeing papers on. So I'll finish there. It's probably not quite 1,000 words. Next slide. This is just looking at the time series for broader latitude bands. So 60 north to 60 south, 35 north to 60 north, 20 north to 20 south, and 60 south to 35 south. It starts out with some ground-based data sets. So all the way back in the 1970s, it picks up adding various satellite records. So we've got quite a few satellite records. Again, the overall thing is a decrease in the 80s and 90s, a leveling off, and a slight increase as we go up towards the present. And again, you can look at the details of this. And there's ozone assessments done every 4 years. If you look up WMO ozone assessment, NOAA is a major partner in developing those assessments and getting the state of the ozone layer. Next slide. So click. Here's the 2018 ozone hole time series, daily time series, looking at the ozone hole. The ozone hole will be the deep blues that develop as the sun returns and ozone chemistry on polar stratospheric clouds take place. And again, the dark blue is below 220 Dobson units. A Dobson unit is a measure of the atmospheric content of ozone. And before the development of the ozone hole in the 80s, we wouldn't have seen values this low above Antarctica. And eventually, the Antarctic polar vortex that has very cold temperatures that allow this ozone destruction, the development of these polar stratospheric cloud goes away and we get mixing back into the atmosphere. Next slide. I think I won't talk about this one in the interest of time. It just shows we do have sensors that are capable of distinguishing the difference in the ozone profiles between outside of the ozone hole and inside of it, and showing that within the ozone hole, we have almost complete destruction of the ozone in about a 5-kilometer layer. It was even larger when the chlorine levels were higher. Next slide. And these are just some postage stamps of year-to-year ozone hole averages for October for the last 40 years. Next slide. The last 18 of those 40, and next slide. So again, I'll finish there and take questions, and we can go back if there's a slide somebody want to hear more about. There are other slides I didn't show. They're available for people to look at from the presentation.
All right, great. Thank you so much, Dr. Flynn. That was just absolutely fascinating and really interesting, just kind of thinking about everything that you presented here today. So thank you so much for sharing that. So at this point, I do want to give an opportunity for people to put their questions and or comments in the chat as people are gathering their thoughts on that. I did want to go ahead and mention that next week, so a week from today on Thursday, March 31st at 12 p.m. Eastern Time, Yingwei Liu, physical scientist from NESDIS STAR, will discuss ice detection from satellites. So I know for me personally, that's definitely something I'll be keeping an eye out for here in the Great Lakes region. So definitely tune back in next week for that presentation. And then I also wanted to encourage everyone here today, please contact the Tower S team, Lee Byerly and Kashad Bowman, for questions about the SBC or for any sort of configuration of satellite products. So please reach out to them, and then you can also chat with them at the Tower S chat room. All right, so it looks like we are starting to have some questions coming in. And one of the earlier submitted questions here, I'll start off with that one, was what factor SPF do you use when you go to the beach?
I use an SPF 35, and I also when I'm out in the sun, I usually wear a hat with a brim to keep the sun off my face. I think we've all become much more aware how important the ozone layer is, and what a good job it does of preventing most of the high energy ultraviolet from getting to the surface. But again, we can do our own parts too as individuals.
So when you mentioned we can do our own parts as individuals, that was definitely one of the questions that popped into my head during your presentation. So can you expand a little bit more on that?
Well, again, you know, the various things that we're already doing sort of by force is, you know, not using these products because most of them have stopped being manufactured. But if you're doing something like getting rid of an old refrigerator, you don't want to just take it yourself to some local landfill. You want to investigate, you know, where someplace will make sure that they take care of the chemicals that might be in that. So old air conditioners, old refrigerators, depending upon how they are, we do want to make sure that we, you know, responsibly dispose of them, just because every little bit that we can stop getting into the atmosphere is quicker recovery for the ozone hole. So
Okay,
following
great.
up on that, is there enough information in terms of the ozone hole is improving? If we can go to the postage stamp plot of the ozone hole monthly averages. Okay, we also have a winner on the Easter egg. So we have a winner on the Easter egg hunt for the slide that was just being showed. So if you can go actually the next one to the one that goes has the monthly ones, there we go. So this shows the onset. So the first slide's here in 79, and you can see there's not a lot of dark purple in those first 4 years for the October averages. And then we start seeing the ozone hole, and then we see it gets very deep by the end of this page here, which is down into the 2000s, where we saw that the amount of effective stratospheric chlorine was peaking. But we also see that if we look back in 2002, there's a pretty wimpy ozone hole. So the ozone hole over Antarctica is created by two things: having high levels of chlorine in the stratosphere and having an isolated polar vortex over Antarctica where very cold temperatures occur. And in 2002, the Antarctic polar vortex broke up early, and we didn't see the destruction as much as we saw, say, the year before. If we go to the next set of slides, which is the last 18 years, the most recent 18 years, we can see that if you could compare these to the other, we're not having quite as strong ozone holes on average. And people track out the depth of the ozone hole, the size of it, and we can explain the variations in the ozone hole from year to year by the changes in stratospheric chlorine that ramp up and is gradual going down, and the year-to-year variations in the dynamics of the polar vortex above Antarctica. So people can fit this with the temperatures, how much of the area had temperatures cold enough to produce polar stratospheric clouds, what the timing of that was, what the isolation of the polar vortex was, what the amount of chlorine was, and explain these year-to-year variations. So it's greatly influenced by dynamics, and we're past this threshold of having enough chlorine that when we do have a cold polar vortex above Antarctica, we're going to get a lot of ozone destruction still, but not as much as we would have 20 years ago, and not as little as we would have, 40 years ago, and not as little as we wouldn't have even seen a full ozone hole 60 years ago.
That's absolutely fascinating. Thank you so much for going into a bigger explanation on that. Appreciate that.
And every year, NOAA puts out a joint, just to the Earth Day question, every year NOAA puts out a joint press release with NASA on right around the time after the peak ozone hole has occurred, the peak in the ozone hole, discussing the various things that are there. Just to make a small admission, I'm a applied mathematician. I'm not an atmospheric chemist. I'm not atmospheric scientist. So they put out a statement, a joint NOAA-NASA statement on what's going on with the ozone hole this year, what's going on with the ozone layer from the perspective of how we're recovering. And as I also mentioned, if you look for the WMO ozone assessments, they have a very good section at the beginning, often a 20 question section at the beginning where they go through the questions people ask and what the good scientific answers to those are, and also an executive summary that summarizes where we are now in the ozone recovery.
Okay, great. Thank you. We've got remark here from Scott, a website showing OMPS data over the North Pole. He says it's one that I look at a lot. So if you scroll up in your chat windows there, feel free to check out that link. So thank you, Scott, for sharing that. And then Victoria asks, is there enough information to determine if the ozone hole is improving?
Yeah, so that's what I was discussing, that again, it is improving. It's hard to see in these monthly averages. You see a hole some years, you don't see ones other years. You see some are bigger, some are smaller. But again, we talk about sort of the potential in the atmosphere for ozone destruction. And if we go back a few slides to the effective stratosphere chlorine one. Here we go. We certainly aren't back even to this 2 parts per billion level of the average amount in the stratosphere. And we're certainly not back to below 1 where we were back in the 60s, but we have come down from this peak. And as was pointed out in the slide, and I didn't mention, we're about a quarter of the way back from where we peaked out to being back at the 2 level, where we'll have gone down where there won't be as much opportunity for as much stratospheric ozone destruction. And again, if we work with this overall amount going up and then coming down, and we look at the specific dynamics year to year in the Antarctic ozone hole polar vortex, we can explain, we can get attribution for why this year was bigger than last year and why it wasn't as big as 10 years ago, even though it was just as cold. So we are seeing improvements. We are able to quantify them. There's some articles out on those, again, where people have matched up the temperature data and the isolation in the winds in the polar vortex with what's going on year to year and these effective stratospheric chlorine amounts.
All right, thank you. Kashad asks, anyone want to take a guess as to what the black spot is on the animation?
And Joseph Patton won.
All right, excellent. Okay,
So again, that was the solar eclipse moving across the Earth as we watch the Earth rotate, but also as the moon was going from one location to another. Again, the Lagrange point is outbeyond the moon, and sometimes the moon actually passes in front of their field of view between them and the Earth, which is a really interesting thing to see. If you look around for epic pictures from the NOAA Discover satellite at Lagrange 1, you'll be able to find ones where they show the moon going across that field of view. But again, you can see the shadow of the moon on the Earth in hourly snapshots.
Excellent, thank you. And nice one there, Joseph, for getting that answer. Okay, so we talked about Earth Day. The next question I'm seeing here is from Selena. The effective stratospheric chlorine shows a peak in the 2000s. This didn't seem to correspond to the 40-year record global chart you showed of total ozone. I don't recall the name of that chart, but can you expand on that?
So if we can go down a couple to get to the anomaly chart. Okay, so again, the peaking we saw was around 2000, and you're right that it doesn't look quite like that here. We don't really seem to see that we bottomed out here. A good part of that is because of, again, when Mount Pinatubo went off, that was a major perturbation of our atmosphere. The amount of sulfates that it put in the atmosphere, which is remarkable, and the destruction on those gives us these very deep views in the northern hemisphere around 40 degrees north. And there also is a temperature dependence to that destruction. So the destruction in the winters peaked. So the 93, 94, 95 winters, depending on how cold they were, saw more destruction from that. So again, I agree that the variations from various other things going on in the atmosphere, we don't really see that it's entirely that way. If we go to the next broader average time series, the next slide. We do kind of see here where we take these bigger zonal means and take out the seasonal effects, that we do seem to see that maybe sometime around 1995 to 2000 is where we see the lowest dip. But we also don't really seem to come up that quickly. And this has been some discussion. There's there's open questions. Ozone is a greenhouse gas, actually. So the loss of ozone actually was a loss of a greenhouse gas in the stratosphere when it was lost. And there's also interactions with water vapor and other things in the atmosphere. So the whole interaction of how climate change from carbon dioxide in the atmosphere is going to interact with our ozone layer, and the ozone layer recovery isn't entirely known. I don't show anything here, but if you go to the assessments, there's lots of plots showing what the models say will happen. And some of them, even some of the models with some of the assumptions, even show an overshooting where we end up in 60 years with more ozone than we had 60 years ago. Most of them don't show that. They show a slight reduction in where we'll end up with climate change with the ozone layer going on. Again, ozone lifetime is affected not just by chlorine, but by the temperature of the atmosphere, by the presence of water vapor. Ozone down in the troposphere has a very short lifetime because of all the water vapor and the warmer temperatures. And the denser atmosphere too, the interactions with the neutral atmosphere.
All right. Looks like here, oh, the next one looks like it was just a remark, perhaps a reference to a song there. Thought the Easter egg was a moon shadow. That was from Michael. And then it looks like might be on to the last question, but we certainly still got a few more minutes if anybody else has anything else. But from Jordan, can you assess the ozone hole using GOES channel 12 or 9.61 microns?
So the we actually not just GOES channel 12, but we don't get very good views from the GOES satellites of the ozone hole because our views are cut off. And just of interest, the Lagrange one does give us more coverage farther north than the geostationaries do. But we do have similar channels on the HERS. We do have similar regions with lots of high spectral resolution channels on the CRIS instrument. So we do have ozone products. The CRIS instrument makes an ozone retrieval as part of the new CAPS retrieval system. We combine that because it has good sensitivity to ozone in the upper troposphere and lower stratosphere. We combine it with the ultraviolet that have good information in the middle and upper stratosphere. And so we put these together to make something we call a TOAST product. The nice thing is, of course, that the IR gives us a polar night. For the ozone hole destruction is actually partially triggered by the presence of sunlight as one of the steps in the chemistry that goes on. So until the sunlight comes back, we aren't seeing a larger ozone destruction. But again, with the IR channels, we can look at the ozone, the Antarctic region or Arctic region in the polar night and get information out there. So we do have products that use that. We do make use of the IR. There are now people who are doing combined retrievals that are taking the retrieval algorithm and giving it both the IR information, say from CRIS, and the ozone information from OPS or other sensor, and developing combined retrievals that put all that information together within the retrieval itself, instead of making two products and combining them.
All right. I am not seeing any other questions coming in at this time. Oh, just as I said that, we had one more here. Hold on. It's from Scott. It says, I'm not sure I followed the reason that you can't use GOES because it does see the poles, albeit at poor resolution. Is the signal lost by the long path from the pole through the atmosphere or some other way?
I believe that at the geostationary orbit, you don't actually see the pole. That your intersection with the Earth might not be too far from that, but again, so we have a very high angle anywhere up there. If you're above 80 degrees, then your angle through the atmosphere again would have to be there, at that, even if you were off at Lagrange 1 or farther. So we have bigger footprints. We have that, so we don't really try to push the GOES ones, partly because we do have the polar ones. And the polar orbiters see the poles very frequently. So 14 times you pass up over near that region, if you've got a wide swath, you're getting very good repeatability and information on those. So I can't say for certain that, you know, it's just that, but we really haven't been trying to push the GOES retrievals for the polar regions.
Okay, and Scott says thanks. All right, I'm not seeing anything else at this time. I will give it 10 more seconds just to see if any final questions come in. But we will certainly be wrapping this up by 12:45 Eastern time here today. Okay, not seeing anything. So at this point, I will just go ahead and pass it back to Jordan. But please don't hesitate to reach back out to the team here if you do have any additional questions to be passed on to our presenter today. And thank you so much, Dr. Flynn. This was great. Really appreciate it.
That was good. Good questions.
Yeah, thank you, Larry and Linda, for moderating today. Very unique topic. Hopefully our field offices learned something. I know I did. So the Satellite Book Club will continue next week with another star scientist, Yingwei Liu from NESDIS Star again. We'll discuss ice detection from satellites, and that will occur at the normal time of 12 noon Eastern time on Thursday, March 31st. In the meantime, please feel free to get in touch with our TowerS team. Lee Byerly and Kashad Bowman can answer any questions you have about the book club or about the configuration of satellite products in AWIPS. For those of you tracking GOES 18, so far so good there. We're continuing to unpack the satellite, if you will, and no issues so far with that. We're looking forward to sharing more about GOES 18 with you on future calls. With that, please take care, and we'll see you again next week. Bye now.